All right. The last talk of the session will be given by Karl Palmskog from KTH, and he's going to tell us about symbolic execution for binary code verification.
Right, so thank you for the introduction. So this is joint work with my colleagues at Uppsala and Intel, and just to point out, a lot of this practical side of the work was done by Andreas during his PhD studies at KTH. So that's there. So before I talk about the kind of binary verification, let me give you some background to this work. We focus on what we usually call unstructured code. This means that you have code that has jumping with labels and so on, and each statement or instruction could have multiple exit points. If you are not careful, then or if you write this manually, you can end up with a can of spaghetti. That's what it's traditionally been called. And you typically don't have a lot of information about typing, or the data is kind of a paucity of types, just machine words, for example. So the thing with unstructured code, it kind of lives as compiler output, for example, and unless you're careful, it could leak, for example, data that you may not want, or have bugs that may not exist at the source code level and so on. It can also be quite difficult to inspect or understand what's going on. So I give this very small example here of an indirect jump where you determine at runtime sort of what function you're calling depending on some value, right? So you're storing the address you're jumping to in some register, and then you're calling some specific instruction here in RISC-V supports this through this JALR instruction, yeah, you sort of do the call and then you return where you came from. So this code, it's also we argue it needs trustworthy verification. So for the classic verification task is translation validation, that you have already verified the code, and now you at the source level, and now you actually need to kind of check that your compiler spit out something that makes sense. But you can also maybe analyze something like execution time bounds in real-time systems. So you may not have a cost model at the level of the language. So maybe you need to do that at the level of machine code or binary code. And there are also other things like low-level security properties, like absence of side channels that you may have to check that may not exist at the source language level. There are certain challenges here. So a lot of things come from kind of what information is missing, right? So you have these things like indirect jumps, where you may have to kind of look at the provenance of the data to figure out where you're heading. You have memory aliasing, and again, not a lot of typing information, and there may be lots of different kinds of code that you want to analyze that are subtly different, like x86 assembly versus RISC-V assembly or something like that. So our contributions in this work, so we propose a general symbolic execution theory for basically suitable for theorem prover use that is adapted for this kind of unstructured code. And we implemented it in the HolBA theorem prover. There was already an intermediate language called Beer that we instantiated this theory for. So that was kind of a concrete programming language. And then there was already tooling around this, so we could translate from, for example, RISC-V to this intermediate language. So we implemented these automatic symbolic executors. So these are kind of programs that apply symbolic execution rules and sort of derive some information about the program. These were different for us for different kind of instruction set architectures due to the different properties we were interested in. But we applied it specifically for RISC-V. We looked at proving these horse-style contracts pre and post condition, and execution time bounds specifically for ARM Cortex-M0. So this is a very simple ARM processor that uses the ARM v7 instruction set. So that's what we did. And so just to give you an idea what this theory is about. So there's kind of a concrete side of the picture. So the theory is general, but we will kind of our target all along was beer, right? So we have a set of labels, and we have some concrete states that consist of a program counter, where you are in this set of labels, and then you have a store, which is some kind of partial mapping of variables to values, and the values will typically be things like machine words of some size, right? And then you have some total and deterministic step relation, which you can kind of repeat, and so you can say like I want to do n number of steps, and this is kind of a restriction versus maybe other fancier languages, right? So some assembly sort of fulfills this. Semantics for ISAs sort of can follow this. And then on the symbolic side, we have a symbolic state where the main kind of addition has become this mapping. The store is now a mapping from variables to symbolic expressions, so it's not necessarily, which may include these symbolic variables of some sort. And then we have path conditions that sort of say what does this represent in some sense? What path in the program does this represent? And then we have an interpretation which maps these symbols to concrete values. So if we want to kind of derive something about the real program, then we have to have this kind of interpretation. And just to give a very tiny example here, so you can sort of, the program is so small here that we don't even show the labels because they're not so interesting, but just have some program that conditionally does some kind of increment. So if you have some kind of initial symbolic state, you may have these symbolic variables alpha and beta that are assigned to these variables. And then you do your symbolic execution, and you end up having two different symbolic states, so one for each possible path condition where, for example, b is equal to 0 is not equal to 0, and one where b or beta in this case is equal to 0. And then you end up with a different symbolic store in each of these states. So that's kind of the game we're playing here. So just to sort of give a very quick kind of rundown of the theory here. So we define something called a matching state. So the symbolic state matches a concrete state through an interpretation if they have the same program counter variable or program counter value, and then you can sort of do this interpretation of the symbolic store and get the concrete store, and then the path condition is true, right? So then for if we want to allow sort of a little bit of deviation from on these variables that may not matter, right? So we have also something called a loosely matching state. If there is this interpretation H prime that is a subset of or H, the original H is a subset of this H prime, and then you have this matching state for that. So this finally gives us the definition of what we call soundness or symbolic execution soundness, and also the definition of our main kind of data structure that this whole formalization builds on, which we call a progress structure. So this consists of a label set and this symbolic state, and then a sort of target set of symbolic states, right? And then so you can sort of relate that to these states, and you say that there exists this S prime where you've taken some steps, and then there exists a corresponding symbolic state which loosely matches this original symbolic state. So maybe it's easier to kind of show this in an illustration. So essentially, for all interpretations, this H and this state that takes this that has this matching. So we start with a symbolic state, and it matches this concrete state, and then there exists some S prime that takes a number of steps in our concrete semantics. So again, doing the actual program executing, and then there exists this S prime symbolic state which loosely matches this original S prime. Okay, so that's the general idea here. So then once we sort of set this up, this notion of symbolic soundness, then we can start to define rules how to derive this. And this is kind of the main ingredient in what we call like a symbolic execution engine. That so these rules are kind of possible operations that you can perform in this symbolic execution engine. And then later we will sort of use these rules in various ways to implement these executors that will automatically kind of symbolically execute the program, and then we can use that information to derive various properties. So these are kind of show the flavor of these rules. So you have some kind of the set of all symbolic successor states, and yeah, this is then you can derive obviously that this is a sound progress structure, and then you can have substitution. So this just is about kind of changing a name, very simple operation. And the condition here is just about kind of not getting things bound when they shouldn't be bound and so on. So some more complicated rules like simplify. So this allows us to kind of manipulate the symbolic store in various ways. You can introduce a new variable that maps to some kind of symbolic expression. And we also have a rule consequence that allows us to, for example, simplify these path conditions and so on. So I'll give you an example, just how you sort of can use this. So for example, if we look at this very simple program that we had before, or sort of the result of symbolically executing that. So we had these two symbolic states, right? One where we had a path condition where beta was not 0, and one where it was 0. And then we can say that, oh, we don't actually want these two different symbolic states. We can sort of merge them together by having a single path condition. But then we sort of lose a little bit. You can see that we lose some kind of information here when we do this. So we just put the alpha in an interval instead of kind of keeping around the information that beta was 0 or not 0. So these are kind of possible operations that we could do depending on what kind of verification task we are interested in. So essentially we implemented sort of a bunch of more rules, and you'll have to look at the paper for all of them, but they are trying to capture all of these kind of common ways of making symbolic execution efficient. And we proved them all kind of sound with respect to in this way I just showed you. And then we sort of implemented on top of this in standard ML. So if you know HolBA, it's basically a theorem prover embedded in the standard ML language. And this means that basically all your proof automation is written as standard ML functions, like building these kind of theorems that are representing the formal proofs. And in this implementation, so the symbolic execution theory is completely standalone, so it could be reused for other purposes, but of course it's very adapted for our use. And again, we use beer as the concrete language here, so it's a sort of general abstract assembly language. And then there were already implementations of proof or sort of semantics preserving translations from for example, RISC-V and RV8 to beer. So we kind of piggyback on that to sort of get things to beer, and then you can symbolically execute at the beer level, and then you can use the results for various things. Okay. So here is the kind of general architecture here. So maybe one flavor that is different from a lot of, so there are many tools that have this architecture, but our goal here was to kind of defer everything to the ISA model, or everything should be expressed in the end in terms of a separate model of the ISA, which in our case comes from this L3 language, which is, for example, used by ARM, I think, in some respect internally. And in this work, we focused on the RISC-V definition, for example, of the ISA. And then we do this translation. So this was done in earlier work to beer. And then further here to the symbolic execution part. And of course, you can also reason about beer manually inside the HOL4. So there are various rules for example, using weakest precondition and so on. But the game here we were playing is that we want to kind of give people actual proof automation instead of manually applying these core logic rules and so on. But you can see here that it sort of feeds into an existing contract theory, which also exists both for at the ISA level and also at the beer level. So somebody had already set this up in earlier work, or subset of the authors of the paper. So essentially, the symbolic execution rules are this, as I said, of operations in this abstract machine, and we implemented these executors, and they are also the ones doing this kind of optimizations that are common in to make symbolic execution scale better. So things like the post-processing pruning and so on. So there, of course, there are rules for pruning state, so it doesn't explode. Yeah, we sort of generate these progress structure theorems, which is essentially a way of saying that, you know, when we kind of run these functions, they produce this HOL4 theorem, which contains the kind of actual data structure itself, but also kind of a witness that it has these properties that we want, right? So usually this is called proof producing in HOL4. So we sort of measure, like, could we actually make this efficient? So I think in the beginning it looked quite bad. Actually, it took many minutes just for small programs, but in the end we got it down to quite manageable times for, you can see here for AES, for example. So you take a few hundred instructions, and it can take up to a minute. So typically how it scales is with the number of instructions, but also with kind of how much is stored in the symbolic memory, right? So for example, if you know your ciphers, you know that they basically all the output bits depend on all the input bits. So there's going to be a lot of operations that you kind of need to keep track of in this symbolic store. So that's why you can see that AES and Cha-Cha take quite a lot of time. Yeah, so we looked at applying this specifically for functional correctness of RISC-V binaries. So again, we leveraged this earlier work on binary contracts for RISC-V and for beer. And essentially, we assume that you start with a RISC-V contract, and then this has to be currently manually translated to beer. This could be automated, but probably for a small fragment of contracts, because essentially now we write them in HOL4. You can write anything, right, using the RISC-V state. And then the idea is that you use these preconditions as path conditions in the beer program, and then you try to prove this strongest post condition, and that allows you kind of to get the post condition. So essentially, yeah, we have already from this library that we use, we have the connection between beer and RISC-V maintained by a simulation relation, which we have as a theorem in HOL4. So here's what it looks like in practice, this proposed verification workflow. So essentially, you don't have to have a source code program, so you could just start with a binary. You don't even have to use disassembly. You can kind of just use the binary directly. But at least I found it a lot easier to work with disassembly, because you can sort of at least see a little bit of what's going on instead of looking at a hex editor or something like that. But essentially, after you have the disassembly, you write some specification for it, and then you translate that to this beer language. And then you run this and get this progress structure, which again is both like a data structure and the theorem, right, that it has these desirable properties. And then you prove automatically this beer contract. And of course, this could fail. So this is not a complete workflow. And finally, you do what we call backlifting, which is taking the beer contract and translating it back to a RISC-V contract. So the whole progress structure to a contract, so this is kind of where the theory meets the practical use. So we have a theorem for that. So essentially, this theorem, so I'm not going to go into too many details here, but essentially just reducing, we assume that we have this progress structure thing, and then we reduce it to proving these three conditions here. And if you can do that, may not be possible for various reasons, then you automatically have this kind of proof of the post condition, right? Okay, so let me give you one small example here. So the easiest example I could think of, which was RISC-V contract verification. So just adding a single instruction. Here is what the precondition and postcondition would look like. So the only kind of discrepancy here is between like the A0 in the assembly and the X10. So this is just like a different name for the same register in RISC-V, right? So you just say that you increment this register by 1. Finally, you get a kind of RISC-V contract after you have done the symbolic execution. And this says that if you start from executing this program at a label and then you stop at a certain other label, then the post condition will hold. So this is just, so we did some case studies here, so I'm not going to go too much into them, interest of time here. But yeah, ciphers, we did SHA-SHA-20 cipher, and we also did some kind of handwritten assembly, just things that are outside what you can prove with verified compilers. And yeah, it takes a couple of minutes to prove that. Maybe I'll skip that. So the other application we have is for execution time bounds. So this relies on this very simple processor that essentially has no very short pipeline and no cache. So essentially, this means that we can have a symbolic variable representing the clock cycle counter, right? And essentially, when you have these two paths, you can have different symbolic paths, and then you can merge them, and then you can use this kind of interval idea to maintain sort of what is the maximum this clock variable maximum value that this clock variable can be, and what is also like the least value that this can be. And this becomes the sort of best case time, right? Or worst case time. And yeah, with this analysis, kind of reduces to this L3 semantics, which was not done by us, basically. So we compare this to testing on hardware and a tool called AIT. So I won't go through too many of these numbers, just to say that we managed to prove for AES, at least for the loop, you have constant time on Cortex-M0. So AIT was actually unsound on this, even though it says the same number of cycles here, actually they count cycles a little bit differently. So this was a bug that we reported, and it was fixed. And we also compare this to just testing on real hardware. So this was another thing. But you can see here that the time it takes can vary between 10 minutes to up to an hour for bigger programs. So this is kind of what we're playing with here. And yeah, so just to compare to other binary analysis frameworks. So again, most of them are not sort of grounded in a theorem prover, but some other works also use. I mean, they usually don't do what we do, which is basically deeply embedding the symbolic execution. So they may use symbolic execution, but they sort of have that outside of the theorem prover itself, which is another kind of set of trade-offs. So we use, and just to point out that we also use a little bit of SMT solver C3 for discharging some conditions here. So we think we got the trusted computing base down a bit, but it can probably shrink even more in the future. And yeah, so that's kind of it. So we have this general theory, and again with these assumptions about labels and deterministic execution and so on, which probably does not hold for a lot of general languages. And we implemented this in HolBA, and we instantiated this for this beer language. And so essentially all these theorems and definitions I showed you, they are all kind of available in HolBA. And you can check on GitHub if you want to see what we did. And essentially, yeah, every verification tasks become just a few like theorem prover files, and that's how it works. And that's it.
Thank you, Karl. Any questions in the audience?
Okay, thank you for the talk. Very cool, I would say. I would like to know, you are basically doing over approximation of the results. If you have the, for example, the timings, you are over approximating the execution time, basically doing an interval between the best case and worst case execution time.
Oh, yeah.
What if the interval is too coarse? Do you have some way to refine this if basically you compute too bad worst case execution time?
Yeah, I mean, so essentially this is like, we have a kind of toolbox, right? So we could implement all these kind of things like coarsening the intervals and so on. So I think Andreas was the one who worked mostly on this execution time stuff. So I think he found some kind of reasonable trade-off specifically for Cortex-M0. But he could probably like play around with it and, you know, if he needed some better approximation or stuff like that, right? So that was one of the points of the work, that this was supposed to be very flexible. We don't commit to a certain strategy. And this was just like one possible approach to doing this execution time stuff.
Okay, thank you.
Any other question? So I have one. So you presented us the different rules that are sound in your system.
Sure.
But then how do you pick and choose the right rules at the right moment so that your analysis is actually effective?
Yeah, so this is, I guess, trial and error was. So again, my colleague Andreas, he worked on this for, I think, many months to figure out, like, you know, what is the best combination of rules to actually make it scale. And I think we had a lot of problems with the symbolic memory just exploding, right? So then you had to implement various ways of pruning and so on. So I think we didn't have, like, there was no, it was mostly a process of trial and error, trying it on actual real programs and sort of seeing where it failed, right?
So you have not found any methodology like for dealing with loops or?
So loops are actually kind of, we consider them a little bit outside of the scope of our work, right? So you can sort of, what we do instead is that we can kind of slice the program and analyze, for example, the loop body and the you know, the loop condition and so on, right, separately. And then this is like the translation validation game, right? So somebody else can do the, you know, the fixed point proof or whatever. So.
Any other question? No? Then let's thank Karl.
Okay.